Test-driven development is a method of writing code that involves writing automated tests first and then developing code to pass those tests. It's widely adopted in professional programming circles and can help lead to fewer bugs being shipped in your code. Now that we have the basics of embedded Rust out of the way, we can start looking at how to apply those concepts. We'll start by seeing how to use test-driven development for embedded code. This can be a little tricky as it often means writing dummy or stub implementations of protocols so we can create automated tests. I'll show you how to create a stub I2C implementation so we can create automated unit tests for our TMP102 driver we wrote a few episodes ago. The basic idea behind test-driven development is that you write your tests before you write your functional code. In the first phase, often called the red phase, you create a unit test around some feature request or bug you wish to fix. You sometimes need to write just enough functional code that the test runs, but it should be failing at this point. You then write functional code such that the test passes. This is known as the green phase. Your code might not be fully optimized, so then you move into the refactoring phase where you rewrite your functional code in an optimized way. This is sometimes called the blue phase. The refactoring process will sometimes introduce new bugs, or you'll often need to tackle a new feature request. So you then do the cycle again, adding a test, writing functional code until it passes, and refactoring your code. You'll often see tests broken out into three categories. The first is unit tests. These are usually simple automated tests that verify the correct operation of individual values, methods, or functions in your code. Next are integration tests, where you verify that larger components operate together. Then you have system or end-to-end tests that verify that everything works together. This is usually where you test the entire application, and it can often be quite time-consuming depending on the complexity of your program. As we'll see, unit tests are usually possible in embedded code, but integration and system tests become much trickier as you either need to automate testing with real hardware, known as hardware in the loop, or you have to find ways to emulate the functionality of low-level drivers like GPIO and I2C. If we're testing our TMP102 driver, we'll need to emulate the I2C driver since we won't be using hardware in the loop. You'll see the following types of substitutions used quite often in test-driven development. The definitions can vary depending on who you ask, but here are some of the terms you'll come across. The first is a dummy. This is when something in the code, like an object, struct, or value, is passed around but doesn't actually do anything. It's just there to fill out parameters in, say, function calls. The next is a fake. These are objects or structs that have mostly working implementations, but they can take shortcuts, which make them not really suitable for production. Then you have a stub. These are bare-bones implementations of classes, structs, or functions that provide canned, predetermined responses to calls. They usually do not respond to anything other than what's needed for the tests. Sometimes you'll see the term spy, which is similar to a stub, but it records information on how the function or class was called or used. Mocks are similar to stubs, but they offer more implementation under the hood. They usually perform some internal checks to ensure that the received values or calls were performed correctly, and they are capable of failing a test from within the implementation. As I mentioned, these definitions can differ depending on who you ask, and they're often used interchangeably with each other. We'll be mostly using dummies and stubs to simulate I2C calls to get our TMP102 driver to work without needing real hardware. By building tests around your functional code, you can easily automate tests to verify your work every time you make updates. This is a crucial step in the continuous integration process, which is half of the continuous integration and continuous delivery or CI/CD pipeline. Even in the embedded world, setting up such a pipeline can save you a lot of headaches by catching bugs early. I recommend checking out my 4-part Intro to CI/CD series to learn more about this pipeline. For now, we're just going to stick with writing simple unit tests so you can see how that works in Rust. Let's add some tests to our TMP102 driver library. So we're going to close down apps. Let's open up libraries, go into our driver directory. We should not need to change anything in cargo.toml because we don't need any dependencies, because Cargo by default comes with a test framework. This is essentially built into the language, or all the things the language gives us when we install it. We will need to open up lib.rs, and we're going to scroll to the bottom to start writing our tests. Let's start by creating this attribute CFG test. This decorates the code directly under it, so this entire tests module. CFG basically says to only compile the code if this particular configuration is set. In this case, we're setting the configuration to test, which Cargo knows how to do that on the back end. This is a special test configuration that gets set whenever we call cargo test, that you will see in a moment when we call that from the command line. Next, we need to import all of the structs and functions that we wrote as part of this driver. So we do that with use super, which refers to the module one above. So that's all of this code we wrote in the previous episode that imports all of it so we can use it in our tests. Next, we need to explicitly link to the standard library, because we're going to be using the standard library as our tests, at least here, will be run on a computer with an operating system, even though in our code we said no standard. So our code can run with no standard, especially for embedded systems, but our tests, we will need the standard library to run some of them. This is useful for things like including strings and vectors and so forth. Next, we'll need a few things from the I2C library in embedded-hal. We're going to need the custom error definitions in there. We're going to alias error as I2C error, so we can reference that appropriately to avoid confusing it with other types of error. We'll need error kind and operation. If we highlight over it, you can get some information. Error kind is an enum. It's a common set of I2C operation errors. And then we have operation, another enum. This holds read and write operations. We will need these for defining our stubs that mimic I2C reads and writes, because the plan is that we're going to replace the I2C bus, because we're trying to run these tests on a real operating system, with some sort of stub or mockup that returns known values when we read and write to something here. So we're going to pass in our mockup of an I2C bus so that these functions can run in our library, and we will return some constant values when we call things like read write, so that our library will still work even though there's no real I2C bus and it's not talking to a real temperature sensor. This allows us to create some basic tests to test our library. Now we actually need to create this I2C stub to mock up or fake our calls to an I2C device. This will be a struct. This should be a public-facing struct because we'll need to call it in our tests. We will have some response data that it returns back. This is just going to be 2 bytes. This will be fake temperature data. And then I'm going to put a call count here. We're not really going to use it. This should give you an idea of how to store things like the number of times something was called if you want to get some metrics from it. But it's not really one of the tests we're going to be performing. Next, we will create some methods to go along with this I2C stub that we're creating. The first is new, which just creates an instance of the stub struct. So in it, we'll fill out some response data with just default of zeros, and we'll start the call count at 0. Now let's create a method that allows us to change the temperature in that response data field in our stub struct. So we can set it to a particular temperature given by a floating point value. Note that we will need a mutable reference to self, the struct itself. And we're going to do the reverse calculation that we did in our library, where we're going to take the floating point value in degrees Celsius. We're going to divide that by 0.0625, cast that as a signed 16-bit integer, shift it over to the left by 4 bits. Then we're going to assign the first element in response data to the temperature raw shifted over by 8 bits, and then cast that as an unsigned 8-bit integer. So that's that most significant byte in temp raw. And then we will assign to the second element of response data temp raw bitwise and with hex FF, so that's that least significant byte, and then cast that as an 8-bit unsigned integer. So now we can modify the temperature that's being held by the quote-unquote temperature sensor, the stub we're creating, and so we can get that data back and verify that the temperatures are equal. And it looks like I want this to be part of the implementation here. So let's indent this under the I2C stub implementation and then actually close out those curly braces. Great, now we have our stub implementation. Embedded-hal requires a concrete type for the I2C implementation. This usually comes from the chip-specific HAL, like our RP235X HAL library. But because we're not using that here, we need to define an actual error type, a concrete error type that gets passed in. We'll also use the derive attribute here so that the compiler automatically fills out the debug and clone implementation for our struct. That way we don't have to create custom versions of those. So we can print out debugging information and we can do a deep copy or a clone of the information in this struct. We need to implement a function known as kind for the I2C error trait. So we will say implement I2C error for dummy error. We will define the function kind. This takes in a reference to self, so that struct, and it returns this error kind where we just take error kind and return other. This is a real basic return. So if we go look at error that we're importing from I2C that we will need to use, if we go to the definition, you can see this is a trait, and this says that this function must be implemented for anything implementing the error trait, which we are doing with our dummy error. And error kind, if we go to that definition, is an enum that allows you to select the kind of error that has occurred. So there might be a bus error, attribution loss, no acknowledge, say from the device, a receive buffer overrun, and then a catch-all for everything else. We're just going to return other as the type and call that good enough for our implementation of kind here. We need to create something known as an associated type here. We're going to use our dummy error type for self error when we're talking about the I2C stub that we're going to implement. An associated type is a bit of an advanced concept that we're not going to go into in detail in this series, but essentially what we're doing is defining a placeholder type inside of a trait. The embedded-hal I2C trait forces us to return a specific error type, usually defined by the chip HAL, like RP235X HAL. We need to create a substitute here so that we can actually return our dummy error instead. This is kind of like an alias, but it's known as an associated type, where we're saying the type of error in this implementation that we're creating should actually be dummy error, which is what we've defined up here. Now we're going to create our stub implementation of the basic I2C read and write functions. So embedded-hal I2C, if we go to the definition here, this is a trait, which means this is an interface, and we have to implement all of the functions listed in here. And it's actually not that many. We have read, write, write read, and transaction. And the reality is we only really need write read because that's all we're really using in our code. The rest of these can just return OK with nothing in it. So that's not so bad for our stub implementation. The read function is going to take in the following parameters. It will need a mutable reference to the struct itself. It will need an 8-bit unsigned integer for the address and a mutable reference to an array of 8-bit unsigned integers for the read buffer. It's going to return a result. The OK of that result is just going to be nothing. This open and close parentheses with nothing in it is known as the unit type in Rust. It represents no meaningful value or nothing. I know I said earlier in a previous episode that Rust doesn't have null or nothing. This is kind of like a nothing, but it is still its own type. You can think of it like a tuple that has nothing in it, just a holder. So result, we have a generic The OK is the unit type, and then we will return self-error, which we defined up above to be this dummy error. So that's how we can get this self-error, even though the concrete type of error is not actually filled out by a HAL because we haven't imported any HALs. If you're curious where we're getting this signature, if you go to the I2C trait, you can find this exact signature given here. Also note that we're putting underscores here, which tells the compiler we're not actually using the parameters, even if anything was passed in. Otherwise, you'll get a warning if you don't include this by convention. Write, just like read, will always return OK since we're not really going to be using it. We will need a mutable reference to self, an 8-bit unsigned integer for the address, and an immutable reference to an 8-bit unsigned integer array. That will be our write buffer. Once again, underscores, meaning we're not going to do anything with those parameters. We will return a result. The OK value will contain the unit type, and the error will just be self-error, even if we're not ever going to return an error from this. And for the actual implementation of this, we will just return OK with the unit type. Next, we're going to implement the write-read method. This is the only function we're using in our actual library, so it's the only one we really care about implementing to test. It will be pretty simple. We're just going to fill out the read buffer with the response data that's stored in the struct, and we're going to return OK. It will need a mutable reference to self. It will need both address and write, again, underscores because we're not going to be using those. And it will need a read buffer, which is a mutable reference to an 8-bit unsigned integer array. Once again, it's going to return a result. The OK value will be just the unit type, and error will be self-error, even if we don't actually use it. We're going to return a canned response. In this case, we're going to fill out that read buffer, where we're going to call this built-in copy from slice function. We'll give it a reference to the response data stored in the struct, and it will do a deep copy of that response data to the read buffer. This is also a good place to demonstrate that we can just increment our call counter here by 1 if you want to look at that to see, for example, how many times this was called. We won't do anything with that here, though. There. And then, as we've been doing before, we'll just return OK with the unit type. And we're actually going to be filling out the read buffer with a canned response, even though we are also returning a canned response. We also need to fill out the transaction details. This will be another canned response of OK with the unit type. This signature is given to us by the I2C trait, and the parameters are a mutable reference to itself, or the struct. We can pass in an address, which is an unsigned 8-bit integer, and then a list of operations. This is an array. It's a mutable reference to an array, and this is of type operation, and it is requiring a lifetime annotation here. So tick underscore is what's known as an anonymous lifetime, or a placeholder. This basically says we're not giving it a name. We don't really plan to do much with it, and just let the compiler figure out what to do with it. So we do need an explicit lifetime annotation here, but since we're not really using it, we're just going to give it some placeholder name. All we're going to do at this point is return OK, because we're not going to be using transaction. That concludes the implementation of our stub I2C bus with supposedly an attached temperature sensor. In fact, we can just call write-read with this stub implementation, and it will always give us the data in response data. You are welcome to flesh this out to make it more like a fake or a fully functioning emulated sensor if you'd like, where you can check the actual device address, you can check the register addresses, and you can even give it functionality to mimic things like triggers if you really want to. But we're going to leave this as being very basic for now so we can demonstrate how to write unit tests. But this should give you a starting point to writing something like a stub where you need to emulate some sort of operation or functionality, especially when you're dealing with embedded systems and you want to be able to test on a computer without connecting up real hardware or doing something like hardware in the loop. So unit tests are usually just basic tests with some example data to demonstrate and ensure functionality. The first one we want to do is just make sure we can create a new driver. So now we're going to be calling code in our actual library, but relying on connecting up to this stub I2C implementation that we just created. So our first test, and notice that we are using this test attribute This tells cargo test when we run it to treat this as one of the unit tests. It registers these tests and it will know how many we have registered and run the tests appropriately. So rather than instantiating an I2C bus like we did in previous episodes using a real HAL and real hardware, we're going to instantiate our I2C stub that we just created by calling this new function, and that just gives us a real basic stub implementation of an I2C bus. Then we're going to instantiate our driver. So now we call TMP102 because that's been brought into scope with that use super asterisk line. We will pass in this I2C stub we just instantiated, and we will set the address to ground. Not that it particularly matters. This should be address hex 48, but as you can see, we never check that in our code above. Rust comes built in with a bunch of these assert macros. They are very useful for testing data or testing information or functions. Essentially, it makes sure that the internal contents are true or evaluate to true. Otherwise, it will crash your whole program and run the panic handler. So you're welcome to use them in your regular programs. Just know that you might end up panicking if something fails. They are very useful in this test framework because rather than completely crashing your program, the test framework will catch the panic and simply just mark the test as failure before moving on to the next test. So you're welcome to use assert here, where you can define your own equality statements or test statements like equals equals or greater than or less than, but they're so common that Rust also gives us this assert equal macro, which we'll use here. So this might be one of our tests where we instantiate it with this default address, assuming that the A0 pin is connected to ground. That should set the internal address in the driver to hex 48. So we can just call this as U8 function from address to make sure that the address is indeed hex 48 because that's what we expect it to be in the hardware. Let's write another unit test. In this case, we will actually attempt to read the temperature using our stub driver. And notice that I'm decorating new functions here. The test framework looks at these functions and will automatically run them on the back end, anything that's marked with this test attribute. As we did earlier, we're going to instantiate a new I2C stub driver, and we're going to create a mutable version of that because we're going to actually change the internal values of it by setting the temperature. Let's set the temperature using the set temperature method to 25 degrees Celsius. If we scroll up, you can see set temperature here, and that should set the internal response data of that struct. That's why we need a mutable version of this stub driver. And actually, this should be I2C stub. There we go, much better. As we did earlier with the first test, we're going to instantiate our driver, pass in that I2C stub struct, and let's also set the device address to hex 48 by sending it address ground. All right, let's read the temperature. We will call driver, which is our actual library under test, say read temperature C, and then we'll just unwrap that result we get from it and set it to temp. As you can probably guess, we want to assert that this temperature we read using our driver that gets read from that I2C stub should be the same as the temperature we set on that fake device, so 25 degrees Celsius. Let's save this. If you're in apps, go up one, go to libraries. Let's go into our TMP102 driver. Make sure you've saved your work. And Cargo makes this really easy. So Cargo test will run our tests after building it. Looks like we've got an error here. And I should take a hint sometimes from IntelliSense when it's yelling at me. It looks like I forgot to actually return self. I forgot to do the thing I promised to do, which is create a new struct, fill out the data, and then make sure that gets returned. All right, let's try that. Cargo test. So it looks like we passed, but we do have a warning here at part 88. And I don't ever remember adding this. So my guess is that IntelliSense filled it out when I was just mashing enter and tab. So let's save that. This is what your test should look like. We're going to start with use super, and we'll leave it at that. So Cargo test. This runs. Feel free to read your results. You can see it running here. And then here are your actual test results. So 2 of them passed. There's also doc tests, which we won't get into. This is for documentation, but feel free to dig into that if you would like. If you want to see what it looks like when one of these fails, all we have to do is change, I don't know, let's fail the first one. We'll change the address because we know that's not right. So run this again. Sure enough, you see test results, 1 passed and 1 failed. Let's change this back to hex 48, save that. And if you'd like to run one test at a time, you can actually refer to them by their function name. So I can say cargo test, give it the function name, let that run, and sure enough, it just runs one test, which is this test temperature read, this one right here. What's interesting is that you don't have to give it the exact name. This is a pattern matching parameter. So we could give it, for example, anything in the strings of the function name, and the test framework will find it. So we could say new, and it'll just run this test for us. It finds test new driver because new is the pattern that matched here. Or we could say test, and it will run both of them because test is a substring in both of the function names. Automated tests play an important role in developing many professional libraries and applications, and I hope this helps you get started writing such tests in Rust. In the next episode, we'll look at interrupts, which serve an important role in many embedded projects. See you then.